Ну вот, давайте я потихонечку буду начинать. Если там еще кто-то подтянется. Хорошо. So some reminder. So let me recall our setting. So we are dealing with GL infinity, which is the Lie algebra of infinite matrices. With finitely many non-zero entries. And we have the universal enveloping algebra, which is embedded into a large object, some algebra denoted by A. Let me recall its definition. So A is an inductive limit of some algebras which are denoted as follows. So M goes to infinity. And here, these algebras are defined as projective limits. Projective limit over N of certain centralizer algebras, which are defined as follows, is by definition the centralizer of the Lie subalgebra. And A sub n finally is the shorthand notation for GLN. And this is the, I'm sorry, Андрей, у меня сейчас лекция, извини, я потом тебе позвоню, простите. I'm sorry, excuse me. And this is the Lie subalgebra of matrices of such a type. And this is the splitting into boxes. Excuse me, I will write. This is M, this is N minus M, N minus M. So this Lie algebra is isomorphic to GL N minus M. Okay, so this is the definition. And to make it a little bit more precise, so by definition, what is an element of our algebra? So it's enough to say what is the element of this subalgebra, of this subalgebra, this one, of this projective limit. So by the very definition, the element A sub M is an infinite sequence, is a sequence where we assume N is large enough, say, and such that A with index N lies in the centralizer. So it lies in this centralizer. And there is a compatibility condition, the projection of this element coincides with the previous term in this sequence, and also some important technical restriction is that the degree is bounded by a constant, which does not depend on n, which makes it possible to say that we have a filtration in our algebra. And finally, what is this projection? Projection from one centralizer to another centralizer is defined as follows. We write our element n as a linear combination of ordered monomials. And here ordered means the following. We put the generators from the last rows on the left, and in the middle we put the generators from this. I mean that we have n-1, n-1. And on the right, we put the remaining generators, which sit here on the last column. And the projection means that we projection amounts to removing all monomials which containing some elements from here, or which amounts to the same from here. And what remains, what is survives after this procedure is only something lying inside the smaller algebra. And this is our projection. Let me give some examples. So examples. First of all, I recall that we have an embedding. GL infinity is embedded into our algebra as follows. So if we take a matrix unit, the corresponding sequence is a stable one. And this is for n large enough. Maximum of I and j. And this gives us an embedding. This produces an embedding of the whole universal enveloping algebra into our algebra A. So this is, in a certain sense, a trivial example. A little bit less trivial one is as follows. Some quadratic elements, so some elements of degree 2. They are obtained as follows. We take A sub n is given by the following element, the summation and some quadratic elements. But it's not enough. We need some correction term, which is this one. And note that it depends on n, some coefficient which depends on n. What is obvious, what is not obvious? More or less obvious, easy to see that this element, easy to see, easy is that n indeed is contained in our centralizer once m is large enough. But what we need the compatibility condition. We need to verify this condition. Now let me do that. So we need to show that the difference, by the very definition, we need to show it belongs to the left ideal . I forgot the notation. Maybe it's as follows: left ideal generated by the matrix units in the last column. So something like that. We need to show. It's trivial. We see that the degree is 2, it remains constant, so there is no problem. So this is the key condition, this one. This one. Let's verify. It's not difficult, but you will see the mechanism of reconstruction. This is why I want to explain it in some details. So we write, by the very definition, we can write as follows. Take the sum not till n by till n minus 1. Minus 1. And the correction term of level n minus 1. So this is precisely the element of level n minus 1. But what the rest? And the rest is as follows. And this one. So what we need to show? We need to show that this one is in this left ideal. How to do that? We need to check that is in this left ideal. But how to do that? We see that this generator is in our idea, but it is on the left. So we need just to put it on the right. So we write it's good because this is already in our ideal, but we have to add the commutator. So in the ideal, and this element using the commutation relations for the generator, we can write it as follows: minus so this is again in the ideal. And this one is cancelled due to the presence of this one. So this is the needed computation. So now I recall the result, which I want to discuss, at least briefly. Theorem about the structure of our algebra. Structure of, so we fix M and discuss this algebra. So the claim is this algebra is isomorphic to the zero level subalgebra, which in terms is the algebra of shifted symmetric functions, and times a subalgebra which is the Yangian of size M. So the main point I would like to discuss is how to realize the Yangian inside these projective limit centralizers. How to do this? So let me recall that what is our Yangian? Our Yangian is generated by certain elements with ij from 1 to m. Capital M is a natural number, and modulo some relations. And these relations are conveniently written in terms of a single matrix relation, a RTT relation, and where these T1 and T2 are two copies of a single T matrix, which is a matrix with the entries. And these entries are generated in turn, are generating series of our generators. Plus correct. Okay, so there are some quadratic and some terms are linear, so quadratic linear relations on the generators, which we have to impose in order to get our Yangian. What is also important? Remark that the relations have a local relations are local. What means local? They have the following form. the commutator is some linear combination of terms of the form some degree, and what is important? Important is that the same indices I, j, k, l are on the left and on the right. So it follows, if you have the bound I, j, k, I, l do not are less or equal to m, it follows the same bound on the right, for the indices on the right. And it follows that we have embeddings. Of course, we need to show that these are embeddings, not simply some maps, but this is easy. So we have a nested sequence of algebra, which makes it possible to define the infinite level Yangian, which is the inductive limit or union of these Yangians. So our goal is to, I repeat it, to realize our Yangian inside our projective limit. So to do that, so we want to construct morphism which in terms I recall is a projective limit. So we need to have some morphisms and moreover they should be compatible with the projections. So we need to construct these maps. Is it clear, or maybe some questions? Please ask. Okay. So the idea is as follows. The idea is as follows. We want to assign to our generator something like this. I know. Okay. Of such a type, and plus correction terms, and this is for n which are for any n we need to construct some to assign to our generator something like this, satisfying this compatibility condition. And the procedure is as follows. We take the embedding here, and we employ the projection onto the universal enveloping algebra. And the second row, I mean this one, is given as follows in terms of our matrix generating function. Let me write and then explain. So what is this? This is my matrix, which I like very much. And this means, this means that we have means that to get the image of this element, we have to compute this matrix and take the ij entry of this matrix. How to do this? And I would like to emphasize that this shift is responsible for the correction terms. So without the shift, we would have the following. What is this? And this is and where is my notation for this term, Let me take it. And because of this shift, we get something more complicated. So by using the same argument as in this simple computation, we can write, so we write J. So, sorry. So this is exactly, so this is the definition. So this is the definition of this element. They are the coefficients which appear in the expansion of this matrix entry. So by our definition, by our construction, we want to send and now we want to verify, and we know that this is a morphism. So what we need to check? This is a morphism. That is, these elements satisfy the defining relations. Why? By the definition, because I explained in some previous lecture that if you write, we take such, I think we get a morphism. And next, the shift also preserves our relations because of the very definition of the RTT, where I forgot it, this one. From this form, it's evident because we have here the difference of the formal parameters that we can shift by a constant. So, I'm sorry. So this is indeed an algebra morphism. So this is the first point. The second point, the with small n, which varies, satisfy are consistent with our projection. So we need to show that with respect to our projection, which is similar to the Harishchandra map, these elements are pairwise compatible. And how to do this? Let me simply indicate some key steps. So step one consists in the following explicit formula. Explicit formula, which says that n can be written as follows. some coefficients, some binomial coefficient. And what is important here, these are the elements which are related to the top degree terms. I recall the definition of this. It is given here. Okay. And the top degree term corresponds to r equal to 0, then this superscript is equal to m. So as r is equal to 0, we get the top degree term, and the rest is the collection of the correction terms. So this is step 1, and this is obtained rather easily from the very definition. All this stuff appears because of the shift of the formal parameter by n. And now what? So our goal is to show that to compare what happens if we change the index small n. We need to show that this is in our left ideal. So we need to show that. So how to do? How to do this? Use induction on M. So if M is equal to 1, this is easy because we have these elements are stable. We don't need to prove anything. So we assume in step 2, observe that we have the following formula. Sorry, no. Okay. So we have to, I want to change the upper index M. So this is trivial. This is trivial, this formula. It's trivial because of the very definition of this one. So please look, we separate this monomial from this one. So we get, so this is easy to see. What is not so easy, what is not so evident, but still can be deduced from the definition of our element T is as follows. It's a similar relation, but for the T element. Looks as follows. and something this one. And the next step, so write the similar expression for n-1 state of n. So we write the same. And this gives us a possibility to take the difference. So take the difference between these two expressions. And the same, essentially the same argument is for the quadratic. In the quadratic case, and use the same argument as for the quadratic case. And it gives us the required result. So what is important? Important observation. In that case, we had here simply like this. And more generally, we use the fact that the elements T, I, J, M transform under the operator of commutation with some other matrix unit exactly as the matrix units. And this happens because the similar fact holds for this. And this is shown directly from the very definition. And actually, I proved that when I discussed the Perelomov-Popov formula. So this is the outline of a proof. So we have this main result. So about the structure of our algebra A. So it is isomorphic to the one. And this gives us an alternative, in a sense, alternative approach to the Yangian. We can construct it through this centralizer construction. And finally, because this is the last lecture, I would like to briefly indicate what is behind this picture, what one can prove else. So one topic is differential operators. So let me recall, this fact is holds for any Lie algebra. So we have the identification with left invariant differential operators on the Lie group. Sometimes it's called the Laurent-Schwarz theorem. It's a general fact from Lie group theory. And we want to, and because we say that our algebra is some analog true universal enveloped algebra for n equal infinity, we want something similar. And indeed, this can be done. So the first fact is that in this particular case of GLN, the left invariant differential operators can be defined not on only on the group, but on the vector space of arbitrary matrices, possibly singular. The reason is that these operators have polynomial coefficients. For instance, the differential operators, which corresponds to a matrix units, has the following form: the left invariant. It's easy to verify, and because it makes sense as an operator on the whole matrix space, let's regard it exactly as an operator on the set of arbitrary matrices. And now we want to realize it as an algebra of differential operators on what? On the space, let's the projective limit of a matrix space, which is simply arbitrary matrices of infinite size without any restriction on the entries. So absolutely arbitrary matrices, which is the same actually as the infinite product, doubly infinite product of the copies of the complex numbers. But the question arises, what means a differential operator on such a space? We adopt the following definition. Differential operator on a space of infinite matrices. So what is, maybe it's, I have to say what means this projective limit. I need to define the projections. The projections are very easy. We have some finite matrix space The projection amounts to removing the last column and the last row. And with respect to these projections, the projective limit is precisely the space of arbitrary matrices. So we have the chain of projections. And what is a differential operator? By the definition, it is a sequence of these are differential operators on these spaces with polynomial coefficients of degree, which is bounded by some constant, which does not depend on n, and there is some consistency relation. The consistency relation looks as follows. With respect to projections. But what does this mean? It means the following. Let me write it. Where f is a function, it's enough to consider polynomials on, and this is the lifting. So what this means? We take some function in this space and we can lift it to this space with respect to our projection. And the condition means as follows. Take our function in this space, apply to it this operator, and take the lift in this space. And this should be the same as first taking the lifting and next applying this operator. But actually, one can rephrase this as follows. This is equivalent to the differential operators of level n-1 should coincide with these operators with all terms containing the extra derivatives or removed. So we remove all extra derivatives and we get some differential operators, and we require this condition, which means that the resulting operator, the coefficients of the resulting operators should depend only on the coordinates on this matrix space. The extra coordinate are forbidden. So this is a very special condition. And this gives us something which can be called a differential operators on the space of infinite matrices, and such operator can be applied to cylinder functions. On this metric space. These are functions on this huge space, which depend only on some finite corner. For these functions form a nice space, say polynomials which depend on some corner. This is a very good space, and our differential operators are well defined on this space. And what next? The final step is as follows. So we have the action of a group GL infinity, which is by definition the inductive limit of Gn. So this is the group of matrices of such a type. Something here, which is a non-singular matrix. And then ones on the diagonals and zeros on the left and on the right. This group operates on our metric space, on our space of matrices, and also it operates on differential operators on the left by left shift and by right shift. And then the theorem is as follows. The algebra AM can be identified with the algebra of differential operators, which are left invariant with respect to the left action of the whole group, and right invariant with respect to its subgroup, where is the subgroup of matrices of such a type. So here are some examples. For instance, some reference, maybe I can, some reference is my paper, which is representations of infinite dimensional classical groups, limits of enveloping algebras and Yangians. This is an old paper in a collection, but actually it is contained in my thesis. This is section 2, and my thesis in Russian is available from my homepage. My Institute for Information Transmission Problems, and it's easy just to Google on my name, written as follows, and it is immediate to see a link to my homepage. So what I want to show, some example. So what is the differential operator corresponding to this generator? It's easy to see. This is the matrix unit. It is represented by these differential operators. This is an infinite sum, but it is well defined on the space of cylinder function, because if you want to apply such an operator to a cylinder functions, we have to delete all extra derivatives, the derivatives with large indices. And after that, we get a well-defined differential operators. What is important here? It's important that actually the same index alpha is present in the differential part and in the coefficient part. Likewise, but a little bit more interesting, is the structure of this element. I recall that it corresponds to the infinite sequence like this. And the corresponding differential operators is as follows. It is the sum of three indices and again we see that in the differential part we have all these indices alpha, beta, and gamma, and the same on the left. So our operation of removing the unnecessary derivatives gives us a well-defined operator on the space of some finite size matrices. So this is our only examples. Some proof can be found in this reference. It contains an exposition of one of the first exposition of the centralizer construction, but I recall that there is also other reference is the survey by Molev, Nazarov, and myself in the Uspekhi. In English is Russian Mathematical Surveys. And there is a preprint in the archive. It's easy to find it. And the main topic of this survey is the theory of the so-called twisted Yangians. Twisted Yangians. And what is this? This is a parallel theory in type BCD. That is for orthogonal, for other classical Lie algebras. Orthogonal, these are type B and D, odd or even size and symplectic. type C, Lie algebras. And the idea is to extend the construction, the centralizer construction, to other classical Lie algebra and look what happens in this situation. It's not difficult to extend the construction. Again, using some projections which are similar to the Harish-Chandra homomorphisms. And it's more difficult, but still possible, to examine the structure of the resulting algebra. And it turns out what we get are not the Drinfeld Yangians, but some different objects which are called twisted Yangians. So the twisted Yangians are some subalgebras. So we get some P or C or D Yangian type algebra, which are contained in the GLN or type A Yangian, and they are some subalgebras, and also they are Hopf ideal. It turns out that this algebra, the Yangian, is a Hopf algebra because it admits a nice co-multiplication. But this object do not have a co-multiplication, but instead of co-multiplication, which should be something like this. Don't exist. Instead of it, we have like this. So we have some algebra morphism involving the GLN. Construction is more intricate and again, there is some RTT type in relation, but more complicated. We have some R, we write it S matrix instead of T matrix, some more complicated, the twisted or something. And this is called the reflection equation. And it involves some transposed version of the R matrix, more complicated. And all this can be found in our survey paper, and also there is a book by Molov, which is called this one, this book. It is published by American Mathematical Society and translated into Russian. It's called, the title is Yangians and classical algebras. And finally, there is a recent reprint by myself in the archive. It is about some generalization of a centralizer construction, which produces some new Yangian type algebras. And their structure is still a little bit mysterious, but they share some properties of the Yangians. So I would like to stop at this moment, and I repeat that this is the last lecture. And I will send the problems to all people who want to get some scores. And now let me switch off the recording.